Today, we're diving into an idea that might feel, well, completely backward at first. It's all about what makes a scientific theory truly powerful. And the answer, which comes from the work of philosopher Karl Popper, is surprisingly simple. It all comes down to one little word: forbidding.
So let me ask you, what makes a scientific theory powerful? Your first instinct probably is to say it's about how much it can explain, right? How many different things it covers. That just seems to make sense.
The intuitive answer is that a strong theory is one with a really wide reach. A theory that allows for and explains tons of different observations. It feels right, but it's actually a trap.
Because what if I told you the complete opposite is true? That the real strength, the true test of a scientific theory, isn't found in what it permits, but in the sheer number of things it strictly forbids from ever happening.
This is the paradox we're going to unpack. How in the world can saying no be more scientifically powerful than saying yes? To get our heads around this, we first need to draw a few clear lines in the sand.
So let's draw those lines. We're going to start with the absolute basic building blocks that every theory has to deal with.
Okay, first up, we have what are called basic statements. Think of these as just individual observable facts. Simple, singular claims about something happening at a specific place at a specific time. They're like the individual pixels of evidence we can gather from the world around us.
Now for our first key idea, empirical content. This is simply the collection of all those basic facts that a theory says are impossible. Think of this as the theory's no list. These are its potential falsifiers. The specific observations that, if we ever saw one, would prove the theory wrong.
And on the flip side, we have the logical range. This is everything the theory permits to happen. It's the whole set of facts that do not contradict the theory. It's the wiggle room, the space where the theory says reality is allowed to play.
So you can really picture any scientific theory as just a sharp line drawn across the entire landscape of all possible observations. On one side, you've got the logical range, everything the theory allows, and on the other, the empirical content, everything it forbids.
And this is where we get to the heart of it. Why is that forbidden side of the line so much more important? Let's explore the incredible power of saying no.
To make this super clear, let's use an analogy. A good scientific theory is like a brilliant detective trying to solve a crime. A detective's real job isn't to say who could have done it, but to definitively rule out who couldn't have done it.
Okay, so imagine two detectives at a crime scene. There are 10 people in the house. Detective A points and says, the butler did it. Detective B looks around and says, someone in the house did it. Which theory is actually more powerful?
Well, we can see the difference right here in what each theory permits in its logical range. Detective B's theory allows for 10 possible suspects, which gives it a huge logical range. Detective A's theory, though, permits only one suspect, making its logical range tiny.
So Detective A's theory, because it has such a small logical range, has way more empirical content. It forbids 9 suspects, and that's what makes it so powerful. It is so easy to test. If we find just one shred of evidence that points to the chef, Detective A's theory is instantly busted. It's highly falsifiable. Detective B's theory, on the other hand, is almost useless. It's nearly impossible to prove it wrong.
And this brings us right to a core principle from Popper. A theory's real claim isn't about what it allows. That's just the background noise. Its entire power, its whole argument, is wrapped up in what it says cannot be true.
Okay, so a smaller logical range makes a theory stronger. But how do scientists actually measure and compare this in practice?
They use a few formal methods, and the logic behind them is exactly the same as our detective analogy, just a little more precise.
So scientists have a few ways to do this. They can check if one theory's forbidden list is a subclass of another's, which basically means it forbids everything the other one does plus more. They also think about logical probability. A bolder, more specific claim is actually less probable, which makes it easier to falsify and therefore more powerful. And finally, they can compare a theory's dimension, which is a way of measuring its complexity.
This picture shows that dimension idea perfectly. Imagine a theory that says planets move in perfect circles. That's a very restrictive theory. Now compare it to a theory that says they move in ellipses. Well, that's less restrictive, since a circle is just one special type of ellipse. Because the circle theory forbids all the other non-circular ellipses, it has a smaller logical range. And that means it has more empirical content and is a stronger, more easily testable claim.
So all of this brings us to a really fundamental question. What is the ultimate goal of science? What is it actually trying to do?
Well, here it is. The grand ambition of science isn't to explain everything, but to find theories that are so precise, so bold, that they restrict what is possible down to the absolute bare minimum. The goal is to forbid as much as possible.
So, a powerful theory isn't some wide, all-encompassing net that can catch every possibility. No, it's a razor-sharp sword that bravely cuts away almost everything, leaving only a tiny, testable slice of what might be true.
And that leaves us with a powerful new tool for our own thinking. The next time you come across some grand theory or a big claim, don't just be impressed by what it seems to explain. Ask the more important question, what does it forbid? Because in science, the real power lies in the courage to be proven wrong.